So before we can worry about graphing it, we have to simplify. Now when I'm simplifying, the first thing I like to do is factor. So do all the factoring stuff, and so you can see what that gives us. Each of the quadratics that we had in this particular problem ended up actually being able to factor. And then once we've done that, before I do anything else, I want to actually take care of the division aspect as well. Now remember how to divide fractions. When we divide fractions, we always flip the second fraction, always the second fraction, and then we multiply. And then once I've done that, I can go ahead and write it as a single fraction. And this was our goal. Now you could have actually done the flip and multiply and then done the factoring. I just tend to find this order a little bit more intuitive. But you're going to end up in the same place right here. And now that we're here, we can look to see what's going to cancel out and simplify. So notice what does appear in both the top and the bottom of this fraction. The x minus 4's appear in both top and bottom, and the x plus 2's appear in both top and bottom. Well, that leaves me then with x plus 1 times x minus 5. It got rid of the fraction. There's no more fraction left here. Now, in terms of prepping to graph this, I'm going to go ahead and expand that out. And so if I multiply it out, I end up with y equals x squared minus 4x minus 5. That's what I'm going to be graphing. But this did start as a rational expression. And so I need to include the restrictions here. Remember, the restrictions are anything that would ever have made the denominator equal 0. Well, I got a few different things. Right here I can see two of them. I can see that it's not going to be able to be negative 2 or 4. But if I trace back through my work, well, those are the same ones. But in this line, notice there's a new one that I had in the denominator. Notice the x minus 5 in the denominator, which means that we should have 5 also as a restriction. So we end up finding here that x cannot equal negative 2, 4, and 5. So if you were given this kind of a problem and you're just asked instead, here's an equation, simplify, this then would be your final answer down here. But since that's not all we're being asked to do, we're being asked to graph it, now we're going to have to do a little bit more work. So going back and thinking about how the graph would look, we're looking at a quadratic. How do we graph a quadratic like this? This is really going back ways now. Well, remember how we find the vertex of a quadratic? We have a short little formula for remembering vertex of a quadratic. X equals negative b over 2a. If that's gotten a little rusty, remind yourself, because yes, you are going to need to know that going forward. Quadratics are going to continue to come up. And so we can go ahead and apply that with our x squared minus 4x minus 5. And so the b, remember b is whatever that middle term coefficient is, so in this case negative 4. And a, well, that's the coefficient of the x squared term. In this case, since there's nothing written there, it's just got to be 1. Hence how we end up with this as our formula, a negative 4 over 2 times 1. Well, that would give me, and yes, I tend to try to keep track of that negative, just let it hang out there until the very end to get 2. Now remember what that gave me. That gave me x. So that's the x-coordinate of my vertex. If I know the x-coordinate, how do I always find y? Plug it in. And so I'm going to take that 2 and I'm going to plug it back in to the original equation. That will then let me find y. And yes, that works anytime you know the x and you want to know the y, whatever kind of equation you're working with. And so we do all that work and we find that y equals negative 9. Yeah, we're dealing with these rational equations, but all of a sudden, yes, we got to remember our quadratics. All right, so we now know our vertex is at 2, negative 9. So I can go ahead and plot that point. And then from there, since it's just a plain old quadratic, Notice it doesn't even have a vertical stretch in front of it. A just equals 1. I'm going to make the same old x squared graph as I normally do. So like if I go over 1, I should go up 1. And I do that on both sides. And the whole reason, remember, is since this is an x squared graph, 1 squared is 1. Okay, so if I go over 2 from my vertex, I'm going to go up 4, yes. Because 2 squared, because this is an x squared graph, 2 squared is 4. And similarly, 3 squared gives me 9, so over 3 up 9. What about 4 squared? Well, that gives me 16. Is that going to fit on this grid? Yeah, we can fit that. Remember, I'm counting from the vertexes. I count those out. What about over 5? 5 squared is 25. Is that going to fit on this grid? No. So I can go ahead and draw the curve that goes through it. Now that was just bringing us back to the quadratics, but now I need to bring you back to the rational functions. These reciprocal functions that we've been doing recently. Because remember, I didn't just graph this function, I have to include the restrictions. So how do the restrictions show up here? Well, I'm going to go to x equals -2. I'm going to find that over here, and I'm going to replace whatever is there with an open circle. I'm going to go where x is 4. And I'm going to find wherever the graph is there, and I'm going to replace that point with an open circle. And then I'm going to go to where x is 5, find out where that hits the graph, and replace that also with an open circle. So this is actually what our graph looks like. We have a parabola, but we have open circles at the points of each of those restrictions. All right, now that we've seen what the graph looks like, I can introduce a few more of these subtleties that we get to play with in this particular problem. Let's take a look at the domain and range. Now, domain, of course, is dealing with what? The x values or the y values? Great. So domains are possible x values. Well, remember that anytime we're doing one of these, our restrictions have to be in there. And normally, if I were graphing this, it would be all real numbers, so that's why we can just say it's everything except the restriction. So your domain is just x cannot equal -2, 4, and 5. The same things that we found earlier. But now the range is going to get a little trickier with this one. Range, of course, deals with y. If I did not have any restrictions in this problem, remember what your range would look like. Because range, without any restrictions, we'd say, well, it starts down here at -9, and it's going up from there. So we would normally have said y is greater than or equal to a -9. But we want to see what it's going to be doing here with these holes in the graph. And what does that change along the way? So here's a line through each of those holes. But notice something unusual about this graph. This is the first time we've seen a graph that does this sort of a thing. In this graph, each line that passes through one of those holes, so for instance this top one here passes through this hole, but then notice it actually passes through a point over there. So this y value, which happens to be at 7 here, the graph actually hits 7. It doesn't on the left side, but it does on the right side. So 7 will still be part of our range. And I need to look at each of those other points like that too. So notice, for instance, I still have a point here, and I still have a point here as well. And so when it comes to finding the range here, we actually don't have anything that ends up changing because of those restrictions, because it has two sides to it here. And so our range actually is just what it normally would have been, which is that y is greater than or equal to -9.